Ever since I started my FPV journey around 2 years ago, I always wanted to eventually design a really good flying FPV frame. After spending way too many hours researching FPV frame design, I couldn't resist trying it myself. I am definitely not a professional engineer by any means, but throughout my FPV journey I slowly started learning Fusion 360 and became more and more interested in the engineering side of FPV. At some point I just wanted to challenge myself and see if I could actually design a frame that flies well, survives hard crashes, is easy to repair and doesn't require excessive tuning. Flight performance was always the highest priority. One thing I noticed while researching frame geometries is that most freestyle frames sit somewhere around 65 to 75 degrees. This is largely driven by camera visibility and keeping the propellers out of view rather than optimizing pure flight characteristics. From a flight characteristics perspective, TrueX is generally considered the most balanced geometry. Because all four motors are positioned symmetrically around the center of gravity, the frame behaves more consistently across pitch, roll and especially yaw. So my goal was getting as close to TrueX behavior as possible while keeping prop visibility and distractions in the footage to an absolute minimum. So I eventually settled on roughly an 80-degree arm angle, which allowed me to stay relatively close to TrueX characteristics while still keeping the image clean. Another thing I paid a lot of attention to was maintaining a perfectly centered center of gravity. So throughout the design process, I constantly adjusted component placements and geometry to keep the center of gravity as close to the middle of the frame as possible. And besides the improved flight characteristics, the more forward positioned arms also add additional protection to the already very well protected TPU camera cage. One of the biggest design decisions was the arm interface. I spent a surprising amount of time thinking about how the arms should connect in the center section. The first concept is having the arms directly touch or interlock with each other. This creates an extremely stiff center section with very good force distribution and alignment between the arms. The downside is that these systems usually require more hardware, become slightly heavier and often make arm replacement a bit less convenient. The second concept uses locking plates that clamp the arms together. This keeps the hardware count very low and makes maintenance much easier. But because the system relies heavily on precise tolerances and clamping force, even small inaccuracies can eventually allow arm movement over time. The third option is a hybrid system where the arms partially touch each other while also being compressed by a locking plate. This combines many of the advantages from both concepts but also increases overall complexity and tolerance sensitivity. I decided to go with the locking plate option because mechanically it simply made the most sense to me. It creates a very rigid center section while keeping maintenance extremely simple. The entire arm system only requires 5 screws. So basically I accepted the challenge of working with very tight tolerances in favor of lower hardware count and easier maintenance. Between the locking plates I also added a TPU compression layer. The camera cage actually turned into one of the most time-consuming parts of the entire project. At first I wanted to print the entire canopy as one single TPU part. But because of the print orientation, the side sections created really ugly overhangs and weak layer transitions. So after probably around 20 different iterations, I eventually had the idea of splitting the cage into 3 separated parts, the main canopy and 2 individual camera side plates. This allows the side plates to be printed completely flat on the print bed, which massively improves print quality and strength because there are basically no problematic overhangs anymore. Another major goal with the canopy was camera protection. Modern FPV cameras like the DJI O4 Pro are insanely expensive, so I wanted the side plates to protect the camera as well as possible during crashes, while still keeping the image clean. At the same time, I also wanted to support camera angles up to around 30 degrees without having huge side plates constantly visible inside the footage. With the final design, I managed to get around 27 degrees without seeing the side plates at all. And even at 30 degrees, they're only very slightly visible and not distracting during the flight at all. Another nice advantage of this design is that the side plates are extremely modular. This makes it easy to create optimized mount for basically any FPV camera without redesigning or reprinting the entire canopy. I also spent quite a bit of time optimizing some smaller but important details throughout the frame. One example is the top plate design. Most frames use the same length for bottom and top plates. To me, that doesn't make a lot of sense once you're flying with camera angles between 20 and 30 degrees, because a longer top plate often forces the camera to stick further out of the cage in order to keep the frame out of view. This leaves the camera more exposed during crashes. So I shortened the top plate accordingly and instead used a very robust 3mm bottom plate to better handle impacts. Another small detail is this opening in a top plate, which allows the battery lead to be routed cleanly upwards. At the same time, I wanted to keep the routing as versatile as possible, so the XT60 can also be routed through the frame and exit at the rear. I also mounted the VTX high enough above the bottom plate to create a dedicated routing channel underneath it. This allows receiver wires and antenna cables to be tucked neatly underneath the VTX instead of sitting directly above it, preventing the battery strap from constantly pressing on them. None of these features are particularly groundbreaking on their own, but together they make the frame a little cleaner to build and easier to service. So at this point, the design was finally finished. After more than 80 design iterations, I finally had a frame that I was genuinely happy with. But there was one problem. Up until now, it only existed inside Fusion 360. Would a manufacturer actually be able to produce it the way I intended? Would the parts fit? Would the tolerances work? And most importantly, would the frame actually deliver on everything I had promised myself? Or was this just going to be a very expensive and time-consuming experiment? I was about to find out. In part 2, I'll show you how I found a supplier, unbox the parts for the very first time, attempt to assemble the frame and see whether this project actually works in the real world. See you there.